swimpd.com if you want to have these slides pulled up on your own screens, and the code is ISROOT. Type in those 6 letters and you should be good. I have a synopsis of those notes kind of handwritten up on the board as well if you'd like to follow along there too. All right, let's fire this up. All right, so standard 20, we're going to start diving into what is called hypothesis testing. Unit 6 is on statistical inference, so we've been doing inference on confidence intervals, making an interval estimate using our sample data, so that there is some interval where we are reasonably certain we've captured the true population parameter, whether it's a proportion or a mean. You can also conduct inference by what is called hypothesis testing, writing a set of hypotheses, collecting data, and then using statistical inference to make an assumption about the overall population. Can we accept or reject the null hypothesis? So this standard focuses on writing the null and alternative hypotheses, and then describing how hypothesis testing might go wrong. Those errors in hypothesis testing have specific names. They are called type 1 and type 2 errors. So the null hypothesis is one of 2 hypotheses we're going to be writing throughout the rest of the semester. The null hypothesis, its notation, is given by H sub O, or H naught. H sub O, H naught. Sometimes I just call it the ho. H sub O, H naught, or the ho. The null hypothesis is a general statement or default position that there is no statistically significant difference between 2 different populations. There is no difference. It's the status quo. Assume that nothing has changed. Everything's as it has been and as it should be. There's no statistical difference. There is no change in comparing 2 different populations. Status quo means everything's as normal, as it should be. That is our base state, in other words. If the null hypothesis is where nothing has changed, the alternative hypothesis would be exactly the opposite. Something has changed. The status quo is no longer true. There's what the null hypothesis says nothing has changed, and the alternative hypothesis where something has changed. The alternative hypothesis, its notation is H sub A. H sub A, or the ha. The ho and the ha. The null and alternative hypothesis. If there is no difference for our null hypothesis, then there has to be some difference for our alternative hypothesis. It's an alternative position where something different is happening to our overall population when compared to the status quo. Some new theory about our population is true, rather than an old theory. Describe our null hypothesis. Some alternate theory when compared back to the status quo. That new conjure is called the alternative hypothesis. H sub naught for the null, its notation, and H sub A for the alternative hypothesis. We can describe different hypotheses using one-directional alternative hypotheses or two-directional alternative hypotheses. When we conduct hypothesis tests, they're either going to be for one-directional significance or for two-directional significance. And I have those described using these distributions on the slide here on the screen, as well as over here on the board. One-directional because now our new theory is that our parameter has increased. Our parameter is greater than some given value. If it's greater than, where are you going to put the significance? In which tail, the right tail or the left tail? If it's greater than what you would have expected.
Right tail.
The right tail. Wouldn't the larger values, wouldn't an increase be put in the right tail? Yeah. These are z-scores that are greater than when compared to the rest of a normal distribution, or t-distribution. So if we're testing in our alternative hypothesis that our population has increased in some value, we can describe that increase by shading in the right tail. It's a one-directional change. It has increased by some value, or increased to some new value. So we can test that significance by calculating a test statistic and seeing if it lies in this right tail. Greater than right-tailed significance. Does that make sense? Just the opposite, we can test an alternative hypothesis. We can test to see if there's been some change by saying, all right, instead of increasing, what if it's decreased? What if my parameter is now less than what I would have expected? My alternative hypothesis states that my parameter is less than the status quo, less than what I would have thought or theorized. If it's less than, put that significance in the left tail to test your hypothesis. Less than, left tail. My parameter could have changed somehow for our alternative hypothesis. There's been some change in the status quo for our alternative hypothesis. Things can change by either increasing or decreasing. So we theorize our alternative hypothesis by stating that it is now greater than some value or less than some value, and shade in the appropriate tails for our distribution. Less than goes in the left tail. An increase in our parameter or greater than for alternative hypothesis signifies a right-tailed significance test. Right? We could have increased, decreased, or we could have had simply just some change in. My parameter could be different or no longer equal to some value. This describes what is called two-directional hypothesis tests, or two-directional significance. If something has changed, could it be greater than what you would have thought? If the value has changed, could it be more than what you would have thought? More than what it was previously? Sure. If something has changed, could it be less than what you would have thought? So it could be either bigger or smaller, right? Isn't that both tails? Isn't that in either direction, to the left or to the right? When we set up two-directional hypothesis tests, our alternative hypothesis is that our parameter is no longer equal to, not equal to, some given value. It could be more than what I would have thought. It could be less than what I would have thought. It just can't be the same as it was before. It just can't be the same as what it was before in our null hypothesis. So for two-directional hypothesis testing, our alternative hypothesis is that our parameter is no longer equal to. It could be more than, it could be less than, it just can't be the same as. Can't be no longer equal to some given value. So we test for that significance by putting our significance levels in either tail, either the left tail or the right tail. All right, so far, standard 20, hypotheses. We have a null hypothesis and alternative hypothesis. The null hypothesis is some status quo level, some previously assumed value about our population. The alternative hypothesis is some new theory. Our population has changed somehow. Some new alternative hypothesis we want to test to see if is true or not. That alternative could either have been bigger or smaller, or either or. Either bigger or smaller, just no longer equal to some given value. All right, so let's practice some of these. I've got a couple of different examples and scenarios on these next few slides. We're going to read through the statement and describe what the hypothesis would be that would match this information. Let's practice writing our own ho and ha. H sub 0 and H sub A. So a fast food company advertises that the pre-cooked weight for its cheeseburgers is on average 0.2 kilograms. The company runs regular quality control spot checks that involves weighing a sample of cheeseburgers to see if the burger is either too light or too heavy. They don't want to rip off the customers by not giving them enough protein for the cheeseburger, or they don't want to short themselves too much and give too much away, right? They don't want to give away too much or give away too little. It can't be too light or too heavy. If the sample average weight is different than 0.2 kilograms, we take a sample and those cheeseburgers have a different weight on average than 0.2 kilograms, then that entire batch is scrapped. You recycle it and start over. Okay. So for this example, let's write the null and alternative hypothesis. We're talking about proportions or means. Is this percents or averages? Average. So we're going to describe our null and alternative hypothesis in terms of mu. We put the null and alternative hypothesis in terms of a parameter, either the population mean, since we're doing averages, or in a different case we might come across later, so if we're doing percents, we'll do it in terms of the population proportion P. Okay. The status quo, there is no difference in our sample versus the population. What would the average weight of these cheeseburgers be if the status quo is still in control, still in effect? What would the average weight of these cheeseburgers be if nothing has changed? There is no difference. So wouldn't these cheeseburgers still weigh on average 0.2 kilograms? Now we collect a sample, we conduct a hypothesis test, we want to see if it's either too light or too heavy. How could I describe the alternative hypothesis in that case? What would too heavy be? So it's more than, right? We don't want it to be more than our 0.2 kilograms that we're stating for these cheeseburgers. What would too light be? So we don't want it to be less. We want to make sure that it's the same as 0.2 kilograms. So we're going to test to see if it's anything different than 0.2 kilograms. We're going to test to see if it's more than 0.2 kilograms. We're going to test to see if it's less than 0.2 kilograms. We're going to test to see if it's different, no longer equal to 0.2 kilograms. That makes sense? Hopefully our cheeseburgers still weigh 0.2 kilograms. We're going to take a sample and see if it's anything different for our alternative hypothesis. Hopefully it's not. Hopefully we're not making them too small or too heavy. We don't want to give away too much product for free. Null hypothesis. Assume the cheeseburgers still weigh 0.2 kilograms and test to see if they weigh anything different, either too much or too little. Test to see if they no longer weigh 0.2 kilograms. Okay. Let's try another one. New scenario. Let's write the ho and the ha, H naught and H sub A for this scenario. A ketchup company regularly receives large shipments of tomatoes. For each shipment that is received, a supervisor takes a random sample of 500 tomatoes to see what percent of the sample is bruised and performs a significance test. They want to see, for quality control, what part of the tomatoes is rotten. If the sample shows convincing evidence that more than 10% of the entire shipment is bruised, they request a new shipment of tomatoes. Testing the entire batch would take too long, so they're going to take some sample and see if more than 10% of the sample is bruised. If more than 10% of the sample is bruised, more than likely we got a bad batch of tomatoes, right? So let's write H naught and H sub A. What's the ho and the ha? We're putting these in terms of proportions or means. Is this percents or averages? Proportions. What tells you it's proportions? There's a percent number, right? We're not talking about average weight. We're talking about what part of the sample. In this case, a proportion. So let's put our hypotheses in terms of P rather than mu. The population parameter P. All right. Our null hypothesis is that P is equal to what percent? What percent are we given? 10%. Or 0.1. Let's assume for the status quo that 10% of our sample is bruised. We're testing to see if what is true as an alternative. What's going to cause us to send this batch back? More than. So we're going to assume that the batch is okay until we can prove, based off of our sample, that it's not, right?
Yeah.
So what would our alternative hypothesis be? P is more than. We're talking about one directional significance now, right? We're going to test to see if our proportion of bruised tomatoes is greater than 10%. This is different than the previous example where we had two directional significance. We didn't want the burgers to be too heavy or too light. I want to see if the proportion of tomatoes that is bruised is strictly greater than 10%, meaning that my batch is probably not very good. Assume the tomatoes are okay until you can prove based off of your sample that they're not. Assume that only 10% are bruised and the batch is fine until you can show otherwise. Try writing this one. We've done a couple. You have a third scenario here to read through and write your own hypotheses, the ho and the ha, for this exam. We're doing hypothesis testing for basically the rest of the semester. You got to get good at writing a null and alternative hypothesis. Reading through this, the WHO suspects passengers on a cruise ship might be infected with the deadly coronavirus. I wrote this last year when the world was starting to shut down. Remember last year when those cruise lines started having the virus cases and they traveled from port to port, hoping they could get people off the ship? Yeah. Well, it's been a year since we've been doing this, so now it's kind of crazy. Anyway, the WHO suspects passengers on a cruise ship might be infected with the deadly coronavirus. They randomly sample 50 of the passengers to screen for any symptoms. If their average body temperature is above 100 degrees, they will quarantine the entire ship for 2 weeks. A cruise ship has thousands of passengers. I don't want to take everyone's temperature, so let's take a sample. I can show that the average temperature is greater than 100 degrees. More than likely, my cruise ship is infected with people of the deadly virus. The ho and the ha. Are you writing a hypothesis in terms of proportions or means? Find that first and then describe what the null and alternative case would be. What's the status quo? What new theory might you want to test for and see if that is true? Think about whether this is one directional or two directional. Are we going to have greater than, less than, or not equal to for our alternative case? Proportions or means? Means. You're always going to frame your hypotheses in terms of the parameter, either P or mu, or population proportion or population mean. Your null hypothesis always uses an equal sign next. The average temperature is equal to what? 100 degrees Fahrenheit. That should be our null hypothesis. Your null hypothesis will always start with some statement of equality. Always going to use an equal sign. Now your alternative hypothesis uses one of three symbols. Strictly greater than, strictly less than, or no longer equal to. Either more than or less than. Just can't be the same as what was previously. What is it in this case? Is it greater than or less than? What tells you greater than?
Good.
It's above 100 degrees, right? We're going to test to see if the temperature on average is more than 100 degrees. If it's more than is safe to let people off the ship. Assume people are healthy until you can take a sample and prove otherwise. That's what hypothesis testing is all about. So we're going to assume that people's temperature is fine. We take a sample of people and show that their average temperature is more than that. All right, questions on writing the ho and the ha, H naught and H sub A. Okay. Hypothesis testing gone wrong. We write our hypotheses. We test for significance. Hopefully the results of our hypothesis test match what's actually true about the entire population. But because we're using sampling, maybe we made a mistake. Sampling is random. What if the sample I collected is different than the actual population? That can happen sometimes. Maybe I just got, by random choice, a non-representative part of the population for my sample. I might have made an error. Errors in hypothesis testing have specific names. They are called type 1 errors and type 2 errors. Hopefully, the data that I collect and conduct inference on leads to the correct conclusion about that population, but it might not. So that's a type 1 error. What mistake did he make?
That's a guy.
And he's probably not pregnant, right?
Yeah.
Right? That would be an example of what is called a false positive, right? A false positive. It's like a pregnancy test. It showed up positive, but you're actually not pregnant. That's a type 1 error, or otherwise known as a false positive. A type 2 error. What's wrong with scenario 2, with the picture on the right? She's obviously pregnant. But the doctor, based off the test, tells her she's not. That is called not a false positive, but a false negative. The test tells you you're not pregnant, but you actually are. All right, let's get a little more in depth into type 1 and 2 errors. A type 1 error is notated using this Greek letter, alpha. Looks kind of like a fish. A type 1 error is given by this notation, alpha. It is a false positive in layman's terms. A false positive is rejecting a true null hypothesis. Rejecting the null hypothesis when it's true. You're taking a pregnancy test. What would the status quo be? What would we start with for our null hypothesis when you take a pregnancy test or any medical test like that? The doctor's going to assume that she is not pregnant until they take a test and it shows that you are, right? So the null hypothesis would be that she's not pregnant. Does that make sense? They reject that null hypothesis and they tell that man that he is pregnant. They're rejecting a true null hypothesis. They're rejecting the fact that you're not pregnant and telling him that he is. A type 1 error is rejecting a true null hypothesis. It's true that the null hypothesis is correct. It's true that that man is not pregnant. But they're rejecting that and telling them that the alternative hypothesis is not correct, that he actually is. In other words, it's a false positive. Type 1 error, alpha, rejecting the null hypothesis incorrectly. Rejecting the null hypothesis when it's actually true in reality. A type 2 error, another error you could make is given by Greek letter beta. Make a B, but give it a long tail. Make a B, but give it a long tail. A type 2 error, beta, is what is commonly known as a false negative. A false negative. It is failing to reject a false null hypothesis. A type 2 error is failing to reject a false null hypothesis. Back to this pregnancy example. The null hypothesis, you're not pregnant. The alternative hypothesis, you are. The doctor is failing to reject a false null hypothesis. They're still saying that she's not pregnant when she actually is.
The cabin.
They're assuming the null hypothesis is still true when it's actually not. We're failing to reject a false null hypothesis. I kind of like this chart to help kind of summarize what's going on when we describe type 1 and 2 errors. Okay? Here's the chart that's also on the screen in front of you. You have the conclusion of your hypothesis test. Either you determine that the null hypothesis is still accurate and you accept it, or you determine that the null hypothesis is false and you reject it. Hopefully that matches with what's true in reality about the entire population. In reality, either the null hypothesis was true or the null hypothesis is actually false. Hopefully, you line up right. You say that the null hypothesis is true when in reality it actually is. Good, you did a good job. Your hypothesis test is correct. Or you reject the null hypothesis correctly when it's actually false. Good job, you did a good job. Your hypothesis worked well. Hopefully you got it right. Sometimes you didn't. What if you accepted the null hypothesis when it's actually incorrect? What if you failed to reject a false null hypothesis? We accepted the null hypothesis when we should have rejected it because it was false. That's a type 2 error, noted with the Greek letter beta. That's one error you can make. What if you falsely reject the null hypothesis? I say the null hypothesis is no longer correct, when in reality it actually is. I reject the null hypothesis when it's true. That's a type 1 error, a false positive, denoted with Greek letter alpha. Soon then. All right, a couple other things to keep in mind about alpha and beta are given below. The power of the test, how accurate the test is given by 1 minus beta. The power of the test is correctly rejecting the null hypothesis. If beta is failing to reject a false null hypothesis, the other part, 1 minus beta, would be correctly rejecting the null hypothesis. Correctly rejecting the null hypothesis, telling somebody they're pregnant when they actually are. The power of the test, the accuracy of the test, the strength of the test is given by 1 minus beta. I want to reject the null hypothesis when I'm supposed to. Null hypothesis is false. Beta is failing to reject a false null hypothesis, incorrectly rejecting the null hypothesis. So 1 minus beta, the other part would be accurately rejecting a false null hypothesis. These next two statements talk about the relationship between alpha and beta. As alpha decreases, beta increases, and vice versa. Statisticians, when they conduct a hypothesis test, they have to set their own significance level. They have to select their own type 1 error probability before they conduct the hypothesis test. So wouldn't it be reasonable to assume you want to make a type 1 error less often? I don't want to screw it up, right? So let's make a type 1 error as little as possible. I'm going to decrease alpha. I'm going to decrease the level of a type 1 error. If I decrease alpha, I'm less likely to reject the null hypothesis. I'm less likely to reject the null hypothesis even when I'm supposed to, when it's false. If I fail to reject a false null hypothesis, isn't that a type 2 error? By decreasing alpha, I might have inadvertently increased the type 2 error probability beta. By decreasing my type 1 error probability, I'm less likely to reject the null hypothesis. What if I'm less likely to reject the null hypothesis? What if I'm less likely to reject the null hypothesis even when I'm supposed to, even when it's false? By failing to reject a false null hypothesis, we inadvertently increase beta, and vice versa. All right, let's practice describing some errors. On this next scenario, identify the ho and the ha What is the null hypothesis and alternative hypothesis? Once you've written those down, describe what a type 1 and 2 error would be for this scenario. Here is the common example. Here is the fundamental example that's probably covered in every single stats class from the beginning of time until now. One of the fundamental tenets in the American legal system is that a person who is accused of a crime is innocent until proven guilty. Have you heard that phrase before? Yeah. Doesn't it start off like every single Law and Order episode? I think it might. Anyway, you are innocent until proven guilty. So a local man is charged with murder and is currently standing trial with the verdict being determined by a jury of their peers. What does the jury assume for the null hypothesis? That the defendant is innocent. We assume you are innocent until the prosecution proves otherwise. The burden of proof is on the prosecution. They have to prove the man guilty, right? Because we assume he's innocent to start. So what's our alternative hypothesis? Say it. He's guilty. Defendant is not innocent or guilty. We've got that. Now, hopefully, the jury does the job right. We let the innocent man walk. We put the guilty man in jail. What if they screw it up? What would a type 1 and 2 error be? Okay. Let's go back and look at our notes on type 1 and 2 errors. Rejecting a true null hypothesis. What would that be in this scenario? So it's true about the null hypothesis. The null hypothesis is true. So he is innocent, but we do the opposite of that, right? It's actually true that the defendant is innocent. The null hypothesis is true, but we reject that. We do the opposite of that. We incorrectly say they're guilty, right? So we put an innocent man in jail. We convict when actually it's actually true that they're innocent, but we do the opposite of that. We incorrectly say they're guilty. It's an error. We know they're innocent when we do otherwise, right? We inadvertently put a innocent man in jail. False positive. We come back with the guilty verdict when we shouldn't have. We reject the null hypothesis that they're innocent and say that they're guilty. What would a type 2 error be? This is usually like the more serious, really bad scenario.
Guilty, but they say you're guilty.
You're a guilty man, right? Usually a type 2 error is like the, oh my God, really bad scenario, right? A type 1 error is, they're both bad, but usually a type 1 error you can live with more than a type 2 error. A type 2 error is more serious offense than a type 1 error. What would a type 2 error be one more time? We put a guilty man on the streets, right? We don't send the guilty man to jail. A false negative. We fail to reject a false null hypothesis. The null hypothesis is false. He's actually guilty. We fail to say that they is, put him on the streets. We acquit a guilty person. We acquit. We fail to convict. We're actually guilty. The null hypothesis is false. They're not innocent. We say they are. We acquit a guilty defendant. All right, let me show you what you guys are working on tomorrow. Pause this. I'll give you guys the rest of the time in class today and time in class tomorrow to work some more on this.